Why hello, for your enjoyment and challenge, welcome to 11.4, titled Area of Kites and Related Figures. Here is the formula for area of a kite. It is area of a kite equals 1/2 d1 times d2, where each of those stands for its diagonal. So it's known as area of a kite is 1/2 diagonal 1 times diagonal 2. That will be true for the related figures of a kite. So if you think back to chapter 5, you can think of the flow diagram we had. The kite leads to the rhombus, which leads to the square. So this formula will work on a kite, a rhombus, and a square, even though you also have the formula coming from the rectangle side for the rhombus and square as well. You could just do base times height. But sometimes you don't have all the information you need, and this formula will work as well. First off, we're going to derive this formula so you can kind of see where it comes from using formulas that we have previously proven in this chapter. A kite here, kite ABCD, is the composite figure from, if you draw a line across, if I hit it at its point, there we go, from two triangles, triangle ABD and triangle BCD. So the area of a kite could be those two triangles' areas added together. Well, now let's look at the area of each. So let's look at ABD. It would be, because we've proven the triangle one, 1/2 times the base times the height, which we kind of need here. And we'll just kind of call this point in the middle point E. So the top one will be 1/2 BD, which is the base and the height. Similarly, we may have to rotate our triangle down here. If we continue this line, we can look at the bottom here, the bottom triangle. So it'll be 1/2 times the base, which is BD, times the height, which is EC. So we have this set up. And then we can take our algebra expression here and we can factor out a like term. So we actually have 1/2 BD in both. So we could take 1/2 BD and then our remaining will be AE plus EC. But if we look a little closer, AE plus EC using segment addition from chapter 1 is actually just AC its entirety, so we can write it as that. But notice BD and AC are just the diagonals, and that's where it comes from, 1/2 times one diagonal times the other diagonal. So there it is, which is much more simple than making a composite figure from that shape. With that being said, that's the only new item in this section. You could pause the video, try the 3 sample problems, and then restart it once you completed it. But we're going to move on right here. Here's our first one. Very simply, we just have a kite. Okay, it tells us it's a kite. We're just going to follow the formula. Okay, area is 1/2 d1 times d2. Notice I'm going to write my formula, show good algebra setup. So it's 1/2 times 6, the entire diagonal, times 13, the entire other diagonal, and using some calculation skills, we'll get 39 meters squared. That's it for example 1. We made it a little more difficult in example 2. We have here a rhombus, okay? So also one other thing to note, the 12 only points at this part of the diagonal. That's what it's looking for there. So we're looking for the area of this rhombus. Reminder, some of our information about a rhombus is that from chapter 5, that our diagonals are perp bisectors of each other. So that causes a right angle to be here. And that becomes really useful because now we got this one's 12. We have a hypotenuse of 15, and that's going to get us a remainder here of 9, which is a 3, 4, 5 right triangle. Reduced triangle principle, we have this set up there. So the other thing we do, all right, we need to know is that not only is it perpendicular, they're perp bisectors of each other, so that therefore this one is 9, this one is 12. And then when we follow our formula, 1/2 diagonal 1 times diagonal 2, 1/2 24 times 18, and using some multiplication skills, our area is 216 feet squared. And now we move on to the last one. We're finding the area and the perimeter, actually, of this bottom shape here. So we're going to, for area, we're going to, well, we need some more information here. Okay, so we got 10, we got 13, okay. So knowing this, actually, the perimeter becomes quite simple. 10, 13, 13, 10. So our perimeter is going to be 46. And we don't have any units here, so I'm just going to write P equals 46 units. And our area is going to take a little more work, but not a ton. Remember that in a kite, each diagonal is perpendicular, and one is a perp bisector of the other. So this is going to form a right angle here. So notice I have a 30, 60, 90 right triangle with the hypotenuse being 10. That'll tell me the short side is going to be 5, and the middle side is going to be 5 root 3. Reminder that this is going to bisect here. So this one's 5, and this one will not be 5 root 3. But this one, if I look from the opposite side here, I got a what? 5. Ooh, I have a right angle, so I have a 5 blank 13 right triangle. This has to be 12 to create a 5, 12, 13, or you can use Pythagorean theorem. Once I have that, that really helps me then use my formula. Area equals 1/2 diagonal 1 times diagonal 2. 1/2, one of the diagonals is 10, the other one is 12 plus 5 root 3. And very simply, 1/2 of 10 is 5, and then I will distribute the 5 to both items. And therefore the area is 60 plus 25 root 3 units squared. Well, that one was a little more challenging, but that's all we have for 11.4, area of kites and related figures.